class. I hope you all are ready. So we're going to start the new unit today, that is deflection of beams. Okay, so it's a very simple topic. It's something related to what we have learned before. Okay, so I'll just teach you the concepts behind bending stresses in beams. Sorry, not deflection of beams. We are doing bending stresses in beams. So I want all of you to start writing. Write the heading. I hope all of you have submitted your assignments. Please maintain one notebook for this. Are you able to see my screen?
Yes, ma'am.
Yes, ma'am.
Yeah. So bending stresses in beams. Okay. So the first concept is about what is pure bending or simple bending. So I'll be drawing a diagram. So can you please draw that with me? So let's draw a overhanging beam. So this is your overhanging beam. And you have two loads on this. So this is one load and this is the other load. Both are W. Okay. And A, B. All right. So RA will be equal to W. RB, if you calculate, it's going to be equal to W if the length is L over here and this length is A. This is also A. Okay. And let's name this one as C, D. Okay, so if we draw the shear force diagram for this is how it will look like. So I'll choose another color for this. So same line, the beam length, C, jot the points. Okay. And this is going to be your SFT diagram. Positive, negative. This length is W. All right, this length is also W. And if you draw the bending moment diagram, this is how it's going to look like. Again, mark the points. So you have a negative bending moment diagram, and this value is going to be W into A. Okay, so this is your BM diagram, and this is SF, shear force diagram. I'm writing short form because it's not fitting on my screen. Okay, so if you see this diagram very clearly, have you guys finished drawing? My screen is visible, right? Yeah. Please let me know once you're done. Please use the chat box. I want all of you to be a little more proactive so that we can go a little fast. Are you guys done?
Yes, ma'am.
Okay, so if you see this diagram, okay, let me just show it to you. Yeah, if you see this particular diagram, if just in case if my screen is not sharing, let me know, okay, immediately. All right, so you have this particular diagram, you see the SFD, there is no shear force on the length of the beam AB. Okay, if you see the length of the beam AB, there is no shear force at all, and there's only bending moment. So if the length of the beam is subjected to a constant bending moment, and it's a constant bending moment and no shear force, okay, that means the shear force is zero, then the stresses will be set up in that length of the beam only due to the bending moment. Okay, so this length of the beam, that is AB, is there are stresses developed on the part of the beam that is AB, and that those stresses which is set up on that length is known as bending stresses. Okay, so and this length of the beam is also said to be pure bending or simple bending. Okay, so it's very simple concept. You guys can just write down the definition. Okay, if please make a note of it. If the length of the beam, if the length of a beam is subjected to a constant bending moment and no shear force, okay, then the stresses set up in that length of the beam is due to bending moment only. Okay, so those stresses is known as bending stresses, and that length of the beam, okay, is said to be under pure bending or simple bending. Okay, don't mind my handwriting. It's hard to write on the iPad. Okay, that's the definition. The next topic. Theory of bending. Okay, this is important. Okay, I'll draw the diagram. Okay, before we go for theory of bending, there are some assumptions that needs to be made, okay? On what basis the definition applies to a particular beam, okay? First thing is material should be homogeneous and isotropic. I will not get into the details because of lack of time. You guys already know this. Okay, so the Young's modulus, that is E, is same intention and compression. I'll explain what is this tension. Where does the tension happen and where does the compression take place? Okay, with a diagram, just oh, okay. Next is the transverse sections. Okay, which were actually plane before bending. It will also remain plane after bending. That means the top portion. Okay, so it's also called as transverse section. So bending will take place on the longitudinal section, not the transverse section. The transverse section will remain plane. Remain plane after bending. Okay, the fourth assumption is going to be okay, beam will initially be straight. Beam will be initially straight. Okay, and then I told you the longitudinal filaments, that means the longitudinal section. Longitudinal section is going to bend, okay, into circular arcs. I hope you guys are writing. Please respond.
Yes.
I'm not asking you to switch on your video because anyway, since my internet is a little low, I'll not be able to see the video. So you guys have to respond when I ask you questions. Center of, so there's going to be a common center of curvature. It's not fitting. Okay. You guys are done? So it should be homogeneous, isotropic. Young's modulus of elasticity should be same in tension as well as compression. Transverse section remains plane. Beam initially is straight and the longitudinal section is the one which bends into circular arcs with a common center of curvature. Okay. Next, so last 2 points. So the radius of curvature is going to be large compared to the dimension of the cross section. Only then we can apply the principles of bending stresses and beams. Okay, so the radius of curvature is large. You will understand this with a diagram in a minute. Compared to the cross section. Dimensions of cross section. Okay, and the last point is each layer of the beam is free to expand or contract. Okay, each layer of beam is free to expand or contract independently. Okay, so let me explain. So now the third point is the theory of bending. Please draw the diagram. So I've drawn a beam here. Okay, it's bending. Moment is in this direction, upwards. Okay, so if you okay, so if you see my video, and imagine if this is the beam. Okay, so I'm applying a bending moment here. I don't know if you're able to see my screen. So if you see this, it's bending downwards. All right, that's exactly what will happen. So I've not drawn the full beam, only a section of the beam. Okay, so you have the beam which is moving. So if you see this, it's bending moment in this direction. This as the axis of the beam. This is the axis of the beam. Okay, this is the axis of the beam. And I'm going to term it as NN. It's the midsection. Okay, and this is, just take it as delta X, a small section. Okay, BD. So this is before bending. And after bending, it's going to be this. Just drawing as an I'm okay, and what's going to happen to section A, B, and C? It's going to slant like this. Okay, so A dash, C dash, B dash, and B dash. And what's happening to the neutral axis here? This is how it's going to end. Okay, so if you notice here, this is going to be N dash and dash. All right. So this is after bending. So after bending. Okay.
Ma'am, your
So,
voice is breaking.
oh yeah. Now is it clear?
No, ma'am.
No, it's not clear. 1 minute. There's some signal issue. You can just see.
Yes, ma'am.
Yes, ma'am. Yes,
Yeah.
ma'am.
Has it become better? The audio? No. Is it better now, guys? Will you tell me if it's better now, the audio? Maybe the chat is a little slow. Rohit, Joel, Partha.
Yes, ma'am.
Yeah,
Yes,
am I
ma'am.
clear?
Yes,
Yes,
ma'am.
ma'am.
Yeah, okay. All right, so if you know, see this particular diagram, okay, if you see this diagram, can you notice that there is compression force taking place at A dash and C dash, and there is tensile force, okay, taking place at B dash and D dash. So I told you in the assumptions, the Young's modulus of elasticity remains the same in tension as well as compression. So those are the assumptions that we're going to make. Okay, so when a beam bends, these are the layers. Okay, the layer on the top and there's a layer at the bottom. All right, and then the middle layer is known as the neutral layer. Okay, so you can write NN is known as the neutral layer. So if you notice here, the neutral layer is also bending. Okay, so there are some layers above the neutral layer and there are some layers below the neutral layer. So all the layers which are above the neutral layer will get shortened. So if you notice here, all the layers between this AC, so A dash, C dash is getting shortened. So there is a compressive force compression that is taking place. Okay, all the layers below N dash, N dash there is tension being applied. So that means all the layers are getting elongated. Okay, so above neutral layer, it will get shortened. All the layers will get shortened. Okay, and the maximum shortened is going to be at the topmost layer. Okay, and below neutral layer, it's going to get elongated. Okay, elongated, and the elongation is going to be maximum at B dash, D dash. Clear? Did you guys understand? Okay, and there's something called as the in the assumptions we said that there is a what do you call it, radius of curvature. Okay, so if this is our diagram, okay, you have your diagram like this, A, C, all right, B, D. This is NN. Okay, and sorry, I will take a, a line, okay, say Y. Okay, the distance between the neutral layer and this EF is Y. Okay, we're coming to the main concept now. Okay, and if you're applying load from top, the beam is going to bend. Okay, it's going to be like this. And if this is the radius of curvature, for example, and this is your neutral axis. Okay, this is going to be your neutral axis. One minute. Let me just, and this is your layer which we are considering. It's also going to bend. It's below the neutral layer, so it's going to be elongated. Tension is going to take place. And what are the points here? Let's mark the points. A dash, C dash, N dash, N dash, E dash, F dash, and B dash, D dash. Okay, and the distance between the neutral layer and the layer that we are considering, that is E dash F dash, is going to be y again. It's going to remain as y. Okay, so if I change the color, if I extend this line, I will get the radius of, this is the center of curvature, and the radius is going to be this r. Okay, and the subtended angle, let's take it as theta. Clear? Let's take it as theta. So before we go ahead with the equation, if this is your beam, okay, and this is the cross section of the beam, all right, what do you mean by cross section? This is my beam. See, imagine this is a rectangular section. Okay, so this portion is the cross section. This portion is the cross section. Wherever you cut the beam, the cross section will remain as square or rectangle, whatever it is. Okay, so that is a cross section of the beam. So now, if this is the neutral layer, so don't confuse with this. In 1 mark, generally people make confuse it. And if this neutral layer, so this is your neutral layer, NN, it will cut the cross section also half, correct? Okay, but at the cross section it is not called as neutral layer, but it is known as neutral axis. Okay, so don't confuse this. Neutral axis. Okay, so if I have to calculate the stress variation on every layer, okay, so if I have to calculate the stress variation on every layer, it is directly proportional to the distance from the neutral layer. So I'm not going to derive. So if I have to calculate the stress in every layer, so on the neutral layer, the stress is going to be 0, because it is not going to change. The dimension will not change. Okay, n and n dash is going to be, it's going to remain the same. Okay, but the layers above n dash will contract, and below n dash will elongate. Okay, so it is direct, the stress is directly proportional to its distance y. Okay, so this is important. It's distance from the neutral layer. So you can write that down. Stress in any layer, okay, is directly proportional. Okay, to the distance of the layer from the neutral layer. Okay, so this equation can also be written as sigma by y equal to E by R. So what is R? Radius of curvature. What is E? Young's modulus. So we'll just do one more concept, and then from next class onwards, we'll solve problems. Have you guys written it down? Is it done? Can I go to the next page?
Yes, ma'am.
Okay.
Yes, ma'am.
So the next concept is moment. Explain to you what is. This is your neutral axis, NA. Okay, if this is your neutral axis, and I want to calculate what is the moment of resistance of this particular layer. Okay, and let's take the thickness of the layer as dy, okay, and the distance as y. Okay, so we know already sigma is equal to E by R multiplied by Y, correct? Okay, so if dA is the area of the layer, okay, consider dA as area of okay, cross-sectional area of the layer. So what will be the force? We know, how do you calculate moment? Force multiplied by perpendicular distance. Okay, so force on the layer is going to be stress multiplied by area. Okay, dA. So we know what is stress, E by R multiplied by Y multiplied by dA. So if you so this is on that particular layer. So if you want to calculate the force on the full section of the beam, okay, total force on the full section of the beam, you guys already know this, I'm just doing a recap. You just have to integrate it, correct? Okay, so total force on section, you can just write this down, okay, for 1 mark and all, this will be section of the beam section. Oh, beam section, sorry, instead of writing section of the beam section, you'll just have to integrate this. Okay, take the constant outside. Okay, so when there is pure bending, forces is going to be 0. Okay, so E by R cannot be 0, so Y multiplied by dA will be equal to 0. Okay, so this Y multiplied by dA that you see here, Y multiplied by dA will be your moment of area dA about neutral axis. So this Y dA is known as the moment of area dA about neutral axis. Okay. So due to pure bending, so we were talking about pure bending. What do you mean by pure bending? The length of the beam is subjected to only bending, no shear force at all. Okay. So we saw if there is no shear force, It's under only pure bending, so this is going to be 0. So y into dA is nothing but moment of area dA about neutral axis. So due to pure bending, layers above the neutral axis are subjected to compressive stresses, and the layers below Na is subjected to tensile stress. Okay. Clear? Okay, I'm not writing it down. You guys can make a note of it. All right. So due to these stresses, the forces will be acting on the layers. Okay. These forces will have moment about neutral axis. Okay. These forces will have moment about neutral axis. So the total moment of these forces about neutral axis for a section is known as moment of resistance of that section. So when we solved this part, basically what we're finding is force on each layer. So this is the formula for that, force on each layer. Okay, and if you want to calculate the moment with respect to neutral axis, okay, moment with respect to neutral axis, it's going to be the force is E by R y multiplied by dA multiplied by y you will get. Okay, so it's going to be y squared. All right, and we can consider this as E by R y square into dA. Okay, so this is equal to m. All right, so m can be taken as the same. Okay, I'll write it in the previous section. This can be written as, if you integrate it, okay, take it for the full section. If you integrate it, this part is nothing but I. Okay, so E by R E by R into I. Okay, so this is the main formula now. Oh, we've short the time. 1 minute, just 2 more minutes. Huh? Clear? Okay. So the final formula here is m by I equal to E by R. And what is E by R? Is equal to sigma by Y. This is known as the bending equation. So we'll be using this equation in the next class. Bending equation. Okay. So m is in mm power 4. Sorry. M moment is Newton mm. Just write it down. I is mm power 4. E is Young's modulus, so Newton per mm square. R is mm. I'm not able to write the square. Okay, it's not coming. Okay, mm square. Again, sigma is also mm square. Y is mm. Okay, so keep this in mind. I will take attendance. We'll start with this in on Monday's class. Okay. Karan, UL1, present. If you have given your attendance, you can leave. Okay. Sridhar.
Present, ma'am.
Alan.
Present, ma'am.
Subhash Ram.
Present, ma'am.
Rachel. Tom.
Present, ma'am.
Present, ma'am.
Anthony. David.
Present, ma'am.
Calvin. Brian.
Present, ma'am.
Present, ma'am.
Astel. Jacob. Evans.
Present, ma'am. Present, ma'am.
Present, ma'am.
Praveen. Vishnu.
Present, ma'am.
Present, ma'am.
Jerry. Prashant. Mukesh.
Present, ma'am.
Oh, Jerry just joined. Prashant. Prashant is absent. Mukesh is present. Ashwin.
Present, ma'am.
Rohit. Abhikash. Tarun.
Present, ma'am.
Tarun
Rohit
present, ma'am.
Abhika is present, ma'am.
Tarun present, ma'am.
Sam. Sriram. Sam Anthony.
Present, ma'am.
Sriram. Arun.
Present, ma'am.
Siol.
Present, ma'am.
Jason.
Present, ma'am.
Kristen.
Present, ma'am.
Akash. Febin.
Present, ma'am.
Balakrishna.
Present, ma'am.
Alex.
Present, ma'am.
Mohammed is absent.
Present,
Sam.
ma'am. Sam, present, ma'am. 31%, ma'am.
Partha.
Present, ma'am.
Ajay. Shai.
Present, ma'am.
Jeff.
madam.
Present, ma'am.
Deepak. Harsh.
Present, ma'am.
Deepak.
Present, ma'am.
Sushil. Joel Verma.
Present, ma'am.
Sushil is absent.
Yes, ma'am.
Richard.
Present, ma'am.
Gibson. Mithun.
Present, ma'am.
Gibson Sujit. Gibson Sam.
Present, ma'am.
Present, ma'am.
Harakulpa.
Present, ma'am.
Aditya. Not
Yes,
there.
ma'am.
Yeah. Bijal.
Present, ma'am.
Okay, absentees are 16, 28, and 41. 16, 28, and 41.
Thank you, ma'am.
Okay, thank you. Thank you, guys.
Ma'am, will you share class code? Google Classroom.